I guess I invite now the first session on niobium cathode materials. Is MacArthur.
Okay, so I'm Richard Walton from the University of Warwick, and it's a pleasure to moderate this morning's session and introduce the speakers. We've got a set of talks on cathode materials, and this will then lead before lunch to the Charles Hatchett Award lecture. The way this is going to work, we'll have 3 25-minute talks now before a break, and then the Q&A will follow after the break. So if you have any questions for the speakers you're just about to listen to, save them for the session after the refreshment break. So the first speaker is Mark MacArthur from Novonix in Nova Scotia in Canada. Mark has been developing new methods for scaling up cathode synthesis since 2020 with Novonix, and he's going to tell us about some of these processes and how niobium might be beneficial to cathode materials.
Thanks for that introduction, and thanks very much to the organizers for inviting me and giving the opportunity to speak to you a little bit about what we're doing at Novonix to really revolutionize the world of cathode active material synthesis. Let me start the slides. Oh, there's a clicker. Perfect. Lovely. Okay, so the title of my talk is The Role of Niobium in Novonix's all-dry, zero-waste cathode synthesis technology. And really, this presentation only scratches the surface of how niobium can actually be integrated into our technology. And I'll get into, about midway through the presentation, why that only scratches the surface. But before I begin, here's some really small font legal notices that my lawyer makes me put in every presentation. Everybody has memorized everything on the screen. Moving on. Okay. So who's Novonix? So we are a company that spreads over Canada and the USA. We have 4 sites, 2 of which are in Nova Scotia, Canada, following under the Battery Technology Solutions umbrella. That's where I am. We also have our anode materials business, which falls under 2 sites in Chattanooga, Tennessee, and they are working on scaling the production of synthetic graphite. So Novonix, at its core, is a battery materials, technology, and equipment company providing revolutionary services and solutions to the battery industry that really enable the adoption of clean energy. And as you see on the slide, I'm highlighting where I am. I'm under the cathode materials and UHPC. That is our equipment line of business. We also have another building dedicated to R&D services, which I'll get into more on the next slide. So this slide really outlines our 3 core areas of business. On the left-hand side of the screen, you see a photograph of our 400,000 square foot jewel in the USA focused on anode materials. We're a leading domestic supplier of battery-grade synthetic graphite, and we're working towards making large-scale and sustainable production of synthetic graphite to advance North American battery supply chains. We're strategically positioned to accelerate energy transition through our technologies, and really that really leads me to the next point, which is where I come in, leading the cathode materials work, is all about technology. We are commercializing patented synthesis technology to generate NMC-based single crystal cathode active materials using a process that we have called the all-dry, zero-waste process. We can use this technology to minimize environmental impact while also producing highly competitive cathode materials. And in middle of 2023, we commissioned a 10-ton pilot demonstration facility to really showcase the types of products that we could make in our small area of the world in Nova Scotia. And just very briefly, the right-hand side of the screen illustrates the whole Battery Technology Solutions division. We offer prototype cell service manufacturing as well as battery testing, materials testing, and is really the core of everything we do in our materials businesses. Everything flows through Battery Technology Solutions in order to really understand the materials that we are making at a real fundamental level as well as in a real performance use case. So what we know about the cathode world is that the synthesis is relatively complex. It needs to be simplified, needs to be cleaner. Some notes on the left of information that we all probably already know, just to look at the actual size of the pie that we're dealing with when it comes to nickel-based cathode active materials. In 2024, it's roughly market size of $27 billion US dollars, and that's poised to eclipse $100 billion by the end of the decade. And when you look at the absolute cost structure of a lithium-ion battery cell, between 30 and 50% of that ends up being dedicated to the cathode material. So trying to reduce the cost of that material is actually a big deal. The waste side of the world, when you're generating these active materials, using conventional processing techniques, you're utilizing and generating significant amounts of waste streams. This includes wastewater per ton of cathode active material, depending on the market report you're reviewing. That's anywhere between 3,500 and to 15,000 liters of water that's required. And on the other side, you're making byproducts all the time. In the case that I'm highlighting here, 1 to 2, all the way even up to 4 tons of sodium sulfate waste that's generated per ton of cathode active material that's produced, which is a big deal. It's a benign product, but when you release it into the ecosystem, what happens? When you're scaling up gigafactories worth of cathode materials, it's a lot of material you got to deal with. It's a lot of waste that could potentially harm the environment. So we need to fix that. So our process that I'm showing in the final point provides higher yields at a lower cost. We're not generating any wastewater because it's an all-dry process. And we have the ability to use flexible inputs. And I'll get into that briefly on the next slide. But when I think of the cathode space, really it boils down to 3 steps. You have to get raw materials from the ground, mining, refining. In a conventional sense, you make a precursor cathode active material, or PCAM, and then you convert that PCAM product into a final cathode active material. In my process, we eliminate the PCAM step and directly go from the raw material to the finished cathode active material. So let's dive in a little deeper into what the heck my process actually is. So I'm illustrating here really a comparison flow sheet from the conventional PCAM synthesis, which is called, I labeled a current precursor synthesis process. It's co-precipitation. Typically, you take metal sulfate salts, react them in a continuous stirred tank reactor at elevated temperature, add in some different reagents like sodium carbonate, ammonium hydroxide for pH control, and then you really precipitate out these beautiful, highly engineered precursor powders. From there, there's a whole bunch of other unit operations, which requires energy, it requires people to run the equipment, and each step generates more and more waste. There's phase separation, washing and grinding, et cetera, et cetera. And each one, it generates considerable amounts of processed wastewater as well as metal wastes that need to be dealt with before release, right? Finally, you take your beautiful free-flowing PCAM powder, add your lithium source, and then calcine the whole batch, and eventually get these nice NMC powders. The Novonix process, the all-dry zero-waste process, by contrast, is a huge simplification. We're beginning with flexible feedstock. We're talking metal powders, metal oxides, metal carbonates, and we combine those in a process we call all-dry zero-waste. There may be a little bit of pretreatment, there may not, depending on the chemistry that we're making. But at the end of the day, that combined product is fed into the calcination process. So we're not using any different equipment than is what is already currently available in the industry, and the calcination process downstream is very similar to what you would see in a conventional sense. And again, we're doing this without using any metal sulfates, no complex reagents, no processing water, and we end up getting a product that has comparable performance to a conventionally made NMC cathode powder. So as I mentioned earlier, we established a pilot facility in Nova Scotia, Canada, to demonstrate the feasibility of this process, and really that the core has been really R&D research by partnering through the university. And in 2021, we partnered with Professor Mark Obervac at Dalhousie University to work on these all-dry processing alternative methods to material synthesis. We now have the all-dry zero-waste process patented, and we are employing 20 people on my team working on this all the time. And I just have a few photos to give you a sense of scale of our pilot facility. In the lower left, you can see a photo of our 13.5 meter long roller hearth kiln. And in the middle lower, we have our pilot jet mill that is in our 1,200 square foot dry room facility. So it's large enough to be real, but small enough to still be inexpensive to run. So why would anybody want to do this? It makes a lot of sense from the economics point of view, and these are claims that we already knew, but we really needed third-party validation to understand in full. So we enlisted Hatch Engineering Group to really run a process comparison study of the conventional way of making NMC cathode powder compared to the Novonix all-dry zero-waste process. And the results are summarized in the table on the right-hand side. Really, the CapEx intensity decreases by roughly 30% going all dry, and that's owing to fewer unit operations and actually having a higher calcination efficiency. You're dealing with metals, metal oxides that don't shrink during calcination, unlike metal sulfates, which turn into a metal hydroxide, which is a lot of water being carried around. So your calcination efficiency ends up being higher. In terms of OpEx, we're decreasing the intensity by roughly 50%. Again, fewer unit operations, fewer operators required to maintain the equipment, and lower power consumption, lower waste treatment costs, et cetera, right? So it makes a whole lot of sense to go all dry. And on the environmental side, roughly 27% lower power consumption, decreasing processing water use by roughly 65%. You still need water to cool equipment as you scale, but the water does not touch the powder itself. And there's no ammonia handling requirements or that sodium sulfate being generated. So it makes a whole lot of sense to go in this all-dry, zero-waste stream rather than making cathode the conventional way. So now I want to get into a few case studies. Again, I haven't touched the niobium side. Wait until case study number 2. I promise there'll be some niobium data in here. But I just wanted to highlight some of the great successes we've had making materials by all-dry zero-waste. And this is on a mid-nickel NMC 631 powder. So what did we do here? We followed the process flow sheet that I showed in a previous slide to really generate NMC by all-dry, combining a few different ingredients. And that would be nickel metal powder, a generic manganese powder, and generic cobalt powders in a weight ratio of 60, 30, 10, as one would expect for 631. In a single step, I also combined a melange of dopant materials as well as the lithium source. This is all in a single step. I'm not dosing separately like in the conventional sense. We ran through the all-dry zero-waste process, calcined the material, had some very primitive surface coatings applied to the material, and what you see on the right-hand side is the powder that we get. So this powder itself has very standard, typical properties of a single crystal NMC631. Particle size is on the order of what one would expect for NMC631. The impurity profile is quite low. We'll put that in a coin half cell, and the voltage curve shows that, you know what, it looks like NMC631. We even ran some head-to-head rate testing on our powder as compared to a commercial NMC631, and the results are pretty comparable, right? The rate mapping is competitive, and the longer-term 1C cycle testing at 4.5 volts is pretty competitive. So we were quite pleased with these results, and what we really needed to do, though, was test what these material could do in a full cell to really understand how well our cathode powder could be in real applications. So we turned to our team to construct 1 amp hour stacked pouch cells, and these are the data. So the left-hand side of the slide shows normalized discharge capacity versus cycle of our material highlighted in green against that commercial NMC631 powder. And what we can see is our material, our cells, are very competitive, I would say even an improvement over commercial NMC cathode materials, at least at 25 degrees Celsius and 1C rate. And we can dive into a little bit of why to understand based off of delta V. We use delta V as an analog for impedance growth, and I'm just showing on the top the absolute value of delta V, and on the bottom is the normalized delta V. You can understand now why our capacity retention ends up being an improvement is the impedance control of the material that we generated is better than the commercial product, right? So we're still following these cells along. This is this morning's data at 560 cycles. We're going to wait and see what happens at 25C. We also have some higher temperature testing ongoing. But this gives you an idea of the power of all dry zero waste and making material a different way. So I want to briefly touch on, again, this is just scratching the surface on what niobium can do in an all-dry zero-waste process. We started a project a few months back with CBMM, really exploring NMC synthesis for high nickel case, 811, using our process while also using niobium in a few different ways. We have a lot of testing in progress, but what I have to show today is some of the results we've collected thus far on surface coating. We also have some tests in progress on using niobium being used as a dopant, but stay tuned for another version of this conference for those data. So very similar to the first case study, we synthesized NMC 811 that's devoid of dopants this time in weight percents listed on the screen of an 811 material using nickel powder, manganese powder, cobalt powder, and an 83:6:11 ratio. Where's the niobium come into play? Well, that's down here in the finishing process, right? So we are really filling in the matrix of tests to understand and optimize what we can do to maximize performance by adding the right amount of niobium. So we are screening surface coatings, at least in this case study, 0.1 weight percent, 0.2 weight percent, and 0.4 weight percent of micron-sized niobium oxide as a surface coating. And on the right-hand side of the screen, you can see the beautiful single crystal geometry that we were able to achieve following through this process flow. So I don't want to go into detail on all of these properties on the left-hand side of the screen, but I am referencing everything to a commercial NMC 811, and all of the properties track fairly well. I just want to highlight the particle size is approximately in the right range of what you would expect for a commercial single crystal NMC811. And the impurity loadout is also quite similar. On the right-hand side of the screen, I'm showing coin half-cell metrics for the commercial product in black, a control uncoated NMC811 that we synthesized in dark green, and then the series of other materials. The most remarkable thing I find out of these data is that with only a very small amount of niobium surface coating, you achieve a comparable first discharge capacity to the commercial reference powder, which is always good to see. And we'll return to that in the next slide. So these data are raw coin half-cell measurements done on those materials from the previous slide. And the left-hand part of the slide is the absolute value of discharge capacity. The right-hand slide is the normalized version. And what you can see right away is the 0.1 weight percent niobium oxide surface coating is quite competitive and comparable to the commercial reference NMC811 powder. I find it very interesting that you only need a little bit, a small amount of niobium to make a huge improvement, but there is a limit, and that limit is apparently 0.1. When you go beyond 0.1 weight percent niobium oxide on the surface, you end up having too much material, which actually decreases your capacity retention. But we're going to continue on with this project and continue into full cells shortly. So right now it's just coin cells, but we'll get there. To understand a little bit about why too much niobium isn't necessarily the best thing when you're dealing with surface coatings, we again return to our metric of delta V, or which is our analog for impedance within the cell. So the left-hand slide is no different. It's the same data as the previous slide, only it's just there for reference. And then in the middle, I'm showing again the absolute value of delta V on top, and then normalized version to look at impedance growth within the cell as you cycle under these conditions. Again, we see that the commercial reference as well as the 0.1 weight percent surface coating is very comparable and competitive. But then we start seeing that we do deviate from that line when we start adding too much niobium oxide on the surface. So really that is what is killing these cells, is the higher impedance by having too much surface coating. And we can still optimize how we're putting the material on the surface. It's something that we can always play with, but it seems like we don't really need to go beyond 0.1 weight percent on the surface to have a very positive influence on the performance of this material. So what's still left to do? Well, lots. This is the very early days of a project that we started, I think it was 3 months ago. So we have a lot of other activities that are ongoing that includes using niobium as an effective, I call it a supporting actor for lithium-ion battery cathode synthesis that we are using the all-dry zero-waste process to actually synthesize. So we're using a few different forms of niobium oxide, both micron and nano-sized, as surface coatings. We're also using those two materials as a dopant material to really understand the influence of niobium oxide as a dopant when you really front-load it in the all-dry zero-waste process, combining all of the materials in a single step. And I'm just showing a really, really quick highlight of some early data of what we have seen with niobium oxide, micron-sized niobium oxide as a dopant material within NMC811. And the most interesting thing that I take away from these data thus far is that the particle size of your NMC811 powder decreases as a function of increasing niobium dopant, which is very interesting. You can get a size control aspect out of using niobium oxide as a dopant material in NMC 811 that's synthesized by all-dry processing. So we're going to explore this further and understand a little bit more about the consequence of adding niobium oxide as a dopant material in future. So to wrap it up, what I've shown you today is that we can make competitive materials, cathode materials, using an all-dry process relative to conventional synthesis routes. We have programs that work on mid-nickel, NMC 631, all the way to ultra-high nickel content materials. We're talking 95.5. And we even have programs that are running with zero cobalt. These are the so-called 640 series of materials. What I've shown in the last few slides is that niobium can be used as an effective dopant or coating. And at least for the coating work, there are benefits to the electrochemical performance of the materials when put into a cell. I've also shown that we have our pilot line in Nova Scotia, Canada, so we are generating real quantities of materials. Our average batch size is between 20 to 50 kilos of powder, and we're making different materials all of the time going through our roller hearth kiln. We're also in the process of acquiring key patents in the all-dry zero-waste processing space, so stay tuned for more on that side. And we're establishing critical partnerships both upstream and downstream. CBMM is one of those examples of those partnerships that we've established this year. And yeah, so we are today sampling powders to tier 1 materials, cell manufacturers, and OEMs. And the feedback thus far has been quite positive. So yeah, thanks very much for the opportunity again, for allowing me to speak, and happy to speak more during question period or during one of the networking sessions. Thanks.
Okay, thank you very much, Mark, for an excellent presentation and for sticking to time. Our second speaker this morning is Yunchao Dong from the Anhui Boshi high-tech new materials company in China. Yunchao graduated from Southwest Jiaotong University in 2010, and he's currently vice president of the Anhui Boshi Materials Company, I shortened the name there, I'm sorry, which is focused on producing manganese-based energy materials. So I'll invite you to give your talk now.
Okay. Good morning, ladies and gentlemen. Okay, I'm very glad here have this chance to introduce ALMO. Actually, is lithium manganese oxide, the application of niobium in China. I'm new from Silicon Metal. Mr. Yunchao Dong is also here. Actually, the initial idea is Mr. Dong make this presentation in Chinese and make the translation to save the time. Now I make the presentation on behalf of Mr. Dong. And you are welcome to ask any question during the Q&A section, okay? The presentation is 3 parts. First is about Boshi. Boshi high-tech nickel. Boshi high-tech nickel is the top 1 ALMO maker in China. And the second is market outlook. And the third is live modified manganese-based material. Boshi, actually, we think Boshi is the first high-tech nickel enterprise covering the whole chain for manganese-based cathode material, from the manganese ore to manganese metal and also manganese-based precursor. And for the product, currently the main product is ALMO, lithium manganese oxide. And for LNMO and LRM, now it's under development. And of course, also the recycling of these materials. Actually, in this year, in China, almost more than 600 niobium oxide consumed in China, and the main in ALMO field. And for Boshi, this company started in 2019. The headquarters base is in Chuzhou, just the north of Nanjing. And the current AMO capacity is more than 50,000 tons per year. And they also have a lot of sub-companions. One is Huaibei Tianmao. Huaibei Tianmao, the AMO capacity is more than 6,000 tons per year. And another is Anhui Boyuan, it's focused on the recycling. And recently this year, they also have some new company. One is the Hubei Boshi Mining. For this company, they have more than 20 million tons of manganese ore reserves. And another is Hubei Boyang. For this company, later? Yeah, okay. For this company, they have planned a new production for 280 tons, including manganese-based precursor and also cathode materials. Here is some business data for Boshi. In 2022, the output for Boshi is 6,000 tons of AMO. This is the top one in China. And in 2022, the output is 25,000 tons and almost top one in global. And in recent 3 years, the market share in China for AMO for Boshi is more than from 30% to 35%, and this year almost more than 40%. And the output is almost 40,000 tons AMO. And the end user for Boshi, one is the electric vehicle, especially for the mini electric vehicle, and the energy storage station. And the main application is these three parts, the light vehicles, electric two-wheels vehicles, and the electric tools, and the 3C. The market. Here is actually the output of AMO in China in last 10 years. Actually, 10 years ago, in 2015, the output for AMO is just 21,000 tons. And this year, almost 120,000 tons, almost 6 times in last 10 years. And for Boshi, the market share, this is the market share for AMO in China in last year. For Boshi High Technical, last year is 35% market share, and this year is 40%. And Boshi is also the top one customer for CBM and silicon metal in China. And here also other top 10 AMO maker in China. Most of them are also our customers. Yeah, most of them also our customer. Yeah. And this is optimistic forecast of AMO demand in China. The main application were still electric two-wheels and also 3C and e-tools. And by 2030, the optimistic forecast is almost, this is 410,000 tons. 410,000 tons. The unit is this one, 10 kilotons. And this is the main customer for Boshi. Main customer. One is Wulin. Wulin is very famous in China, especially for the mini EV. They use Boshi's this kind of MO, BAXT MO, cathode material. And ion, they use currently, the cooperative with Boshi use LNMO. And ATL is famous for electric bicycle, electric motor in China. They use Boshi's this one AMO. And the 3C companion, EVE, they use this kind of Boshi AMO material. Okay, now we would like to share our understanding for niobium in AMO in China. Actually, it's now already widely accepted by AMO maker in China. Here is imagine of different material, different cathode material, the voltage and the capacity, and currently Boshi, the main product is AMO. And in the future, one developed direction may be the high voltage AMO. Another direction is high capacity AMR, or some people may call it RM or OLO, lithium-rich manganese or cathode materials. So this is the three main topics we will discuss today: AMRO and ANMO and RM. For AMO, of course, there's a lot of benefit for AMO. One is the three-dimensional lithium diffusion channels, and also very nice, excellent rate performance, very low cost because manganese is very rich in the earth, and high safe, no poison, and environment friendly. Of course, AMO also faces some challenge. One is the cycling stability due to the manganese dissolution, reaction with HF acid, and the jet distortion, and also particle creation during the cycling. Let's see, niobium, what kind of rule niobium could enhance to solve to improve some performance for this point. One is we are interested in once we added niobium into MO, what kind of phenomena we could observe. This we think is the most important phenomena we observed. Once we added the niobium into the MO, whether it's doping or coating, it depends on the temperature or the time, and also content. If we added the niobium from this content to this content, the main phenomena we could observe is the morphology change from the octahedral to polyhedral, and also spheric-like. This is, I think, for MO, is very important phenomena for MO. We will discuss it in detail later. Okay. And this is one project we cooperated with Fudan University. If we added 1% different element in MO, we could find only niobium have the absolutely the greater influence on the morphology. This is that's why the MO industry maker quietly accept niobium in China. Okay, and another phenomena is people usually could find lithium niobate once you added the niobium in MO. This is one project we cooperated with IOP in China, Institute of Physics in China, and they coat MO by different temperature and different niobium oxide content, and they could find lithium niobate. And also, this is also the evidence. That means when you add niobium oxide in MO, you could form niobium, lithium niobate carve the particle. Another phenomena also very interesting is when you added niobium with different content in MO, the particle size also changed, especially for D10. That means when you add the niobium, the D10 particle size increased a lot. This is very interesting. Maybe some professor will show some data in NCM. Niobium will refine the primary particle size. What's the reason? It's very interesting. But here, once we increase the primary particle size, you can increase the compacted density. Yeah. Of course, in NCM, if you refine the primary particle size, you can increase the mechanical performance of the particle. It also could increase the rolling pressure and also can improve the tap density or something. Okay, let's make share our standing. Maybe it's not quite correct. It's some general understanding for niobium ruler. Why we could observe this phenomena in AMO? Of course, the first is niobium changes the morphology a great. And what's the benefit for this change? First, as people know, first for the niobium-free MO, the lattice plate is this 111. And if we increase the niobium, we can get almost a spherical-like shape. And this shape has a lot of benefit. First is you can get a small BT. The surface decreased. With the same volume, this shape and this shape, this one has a small BT. So you have less side reaction and then the less manganese dissolution. And this phenomena compared with this one, you have a higher compacted density. You can increase the compact density. And for lithium diffusion, in different phase, different plate, different lattice plate, actually, in this one and also this one, they have the diffusion is faster compared with this plane. So you can increase the, decrease the powder resistance. Yeah. Okay, let's show some data. Here is manganese dissolution without niobium and with niobium modified. And 7 days, we can find the manganese dissolution decreased 70% even at this temperature, at high temperature. For AMO, high temperature, the cycling stability is also very weak point for this kind of material. And here, the compacted density with niobium increase, the compacted density also increased. And this one is the powder, powder resistance decreased. Here increased more than 10%, and the powder resistance decreased more than 60%. And the discharge capacity here, with niobium increase, this discharge capacity increased more than 10%. And the cycling performance increased from this one, 92 to 97. And for high temperature cycling performance, this is the work we cooperate with the IOP. They just coat the AMO material by 0.25% or 0.5%, and coat at this temperature and tested at 55 degrees. We can find with niobium modified, the capacity orientation increased from 87% to, this is 1992? And here we show the commercial product by Boshi, 2 types. One is high power type, another is high capacity type. For the first discharge capacity, there are more than 150, and here is 120. And for the first discharge efficiency, higher than 95%. Yeah. This is the typical commercial product from Boshi. Okay, let's move to LNMO. Based on the understanding of niobium ruler in AMO, it's easy to to think, niobium also could play a similar role in LNMO, although it's a high voltage LNMO, because in LNMO, the manganese dissolution is also a problem, serious problem. And actually, for this kind of material, people also use doping, coating, or the morphology control and size control to improve the performance. And here is the, this is the data from Boshi for LNMO. They developed, they could find the very thin niobium, lithium niobate coating layer. And for the performance, this is the cycling performance of niobium modified. This is at room temperature and have a higher temperature, 45 degrees. And this, both of these are niobium modified. And compare with without niobium modified, this one increased 6%. And this one increased 30% respectively. And we also, of course, actually a lot of basic parameter for niobium and also niobate. We are still need to do more work to investigate this general performance. One is niobium with oxide, with oxygen, the bond is the most strong one compared with this element. This is also very helpful to stable the structure and also improve the safety. Okay, another is the third one is the AMR. For AMR, of course, actually there's a lot of chemical composition, a lot of structure, or a lot of chemical structure for this kind of material. And also a lot of research work also revealed the niobium ruler, for example, for the help how to the voltage degrade and the poor capacity orientation and the road later performance, and also how to due to niobium the how to strengthen TMO bond, the stability of the redox chemistry, and also less oxygen evolution, and the degradation. And for Boshi, this is one case, the modified the MR. They actually is use niobium together with alumina. This is also very popular in China. Niobium plus alumina or niobium plus Mg in, for example, in AMFP, and sometimes maybe titanium. Yeah. And they also found on the surface, you could find this kind of the niobium layer. And here shows some performance for they developed. Okay, this is without niobium, and this is with niobium and aluminum, and also the discharge capacity. We can find after 150 cycles, the voltage, the decrease is reduced. The decrease is reduced, and for the capacity, niobium and alumina modified is quite better compared with the not modified by niobium. Okay, that's almost the understanding we would like to share with all of you. We would like take this chance to introduce the lithium LMO material in China it's already very, the output is also very large, and the niobium application also quietly accept the rule and the mechanism quite accepted by China industry. And we also would like suggest if you are considering, because this is also very low cost and with a higher performance, and actually in China, we also some information feedback from the EV company. They want to make utilization of this kind of material more, even for EV, for the power battery. So if you have chance, maybe please take more attention to this kind of material in China. Okay, thank you.
Thank you very much for another great lecture. So now the third speaker in this session before the refreshment break is Professor Yang-Kuk Sun from Hanyang University in South Korea. Professor Sun is an expert in materials chemistry and chemical engineering and has worked on many types of energy storage materials over the years. And this morning he's going to tell us about recent progress on how niobium can be used for high nickel cathode materials.
Okay, thank you, Chairman. First of all, I would like to thank the CBMM organizing committee for inviting me to this beautiful conference. And my title is Research Progress on the use of the niobium for doping and coating for high nickel cathode materials. This is content of my talk. First, I would like to talk about the major issue of nickel-rich NCM and NCA cathode materials. And as you know, this is the intrinsic, the general characteristics of the NCM cathode materials. As you can see here, with increasing the discharge capacity and the capacity by raising nickel content and the capacity tension and the thermal stability accordingly decreased. Based on this result, it is impossible to develop ideal cathode by just changing the chemical compositions. And however, we need a cathode material at this point with high capacity, good cycle life, and safe materials. And before that, we should know the capacitating mechanism of nickel-rich cathode materials. And as you can see here, this is the data was carried out by in-situ XRD. And as you can see, the unit cell volume monotonously decreased to up to 4.1 volt, and then rapidly decreased and above 4.2 volt, which is corresponding to a factor of the H2H3 phase transitions. In addition, you can see the unit cell volume variation is increased with increasing the nickel content, this one. And for example, this value is 4.3% for 622, almost 10% for pure LNOs. And I believe that the anisotropic volume contraction caused the micro-cracking of the cathode. To confirm this hypothesis, we observed the cross-section of the various different kind of cathode material after charge to 4.3 volt after fully charged. As you can see, the NCM-A11 contains some micro cracks in the particle interior only. However, in the NCM-90 of LNO cathode exhibited the increased amount of micro crack, which is well propagated to particle outer surface. And it is very well known that the parasitic reaction of the the valent nickel with electrolyte produce nickel oxide like a rock salt impute layer on cathode surface. And with increasing nickel content, the damage is increased. This is a capacitive fading mechanism, and the formed microcracks resulted from the anisotropic volume contraction propagated to particle outer surface and facilitating electrolyte infiltration along the formed microcrack into particle interiors, and which accelerate the surface degradation primary particle inner primary particle by reacting tetravalent unstable tetravalent nickel with electrolyte to form nickel oxide-like impurity phase, and thus gradual capacitive fading during the cyclings. And this is there are two intrinsic property of capacitive fading of nickel-lithium materials. And this is the one is microcracking, the other is residual lithium compound issues. And as I explained before, microcracking continuously leads to capacitive fading by the increasingly forming the rock salt impurity phase in the particle interiors. And the other issue is residual lithium compound that easily decomposed and lead to cell swelling, which result in the capacitive fadings. And this is the characteristics of the rod-shaped cathode materials. As you know very well, conventional cathode composed of large polygonal shaped primary particles. This material can easily develop significant microcrack during the induced by the internal stress during the charging process. In comparison, rod-shaped primary particle can easily dissipate internal stress and thus minimize microcracking. And let me introduce microstructure controlled NCA cathode by the niobium dopings. As explained, as you know very well, NCA, conventional NCA, NCM cathode composed of radially oriented, large polygonal shaped primary particles. This material, as explained before, this material suffers from the huge microcracking during cyclings. However, this microstructure can be modified by the X doping, including especially niobium doping. The modified cathode material composed of radially aligned long rod-shaped primary particles. And therefore, we prepared 4 different kinds of cathode materials, and one is a CS-type NCA cathode with a nickel content 94% as a baseline material, and then we doped zirconium with zirconium, niobium, tungsten, denoted as XCS NCA cathode material. This is a comparison of microcrack correction and mechanical strength of the prepared cathode. And as you can see here, all the prepared cathode composed of nanorod primary particles. And after the 100 cycles, as you can see, niobium doped cathode material shows the least areal fraction of microcracking. This value is 2.8% compared to others. And also, mechanical, the niobium doped cathode has the highest mechanical strength of around 200 megapascal compared to others. And as you can see, the unload test result, the niobium doped cathode can tolerate pulverization up to about 200 cycles, whereas the baseline and tungsten doped cathode material in the collapsed after 92 and 169 cycles respectively. And based on this result, we believed that improved mechanical strength of the niobium doped cathode can suppress electrochemically induced microcracking and thus improve the cycle life, long-term cycle life. And this is the TEM-ADAX mapping and the line scan image. And as you can see here, indeed the mapping and the line scans. And as you can see, zirconium ion is homogeneously distributed throughout the particle, whereas niobium and the tungsten ion is segregated at the grain boundaries, and especially in the niobium ions. And also the nickel concentration difference of between core and the surface over the baseline and the zirconium doped cathode rapidly decreased with increasing calcination temperature, whereas niobium doping is considerably maintained nickel concentration difference up to even at the calcined 740 degrees Celsius compared to others. And this is the relationship, the cycling stability and the microcrack fraction and the crystallinities. And as you can see here, this is the baseline, the zirconium, niobium, and the tungsten doped material. As you can see here, the cathode having the smaller error fraction of microcracking demonstrate the higher the cycling stability and indicating morphological pitch is more important than the crystallinities. And based on this result, as you can see here, niobium doped cathode shows the best cycling performance in half cell testing. And this is a long-term cycling stability of doped cathode as prepared and washed state. And in full cell testing, as you can see, again, niobium doped NCA, CS NCA cathode exhibited the best cycling performance. After the washing, in order to improve the cycling stability, we washed niobium doped NCA cathode. After washing, as you can see, the cobalt washed cathode exhibited further improvement in long-term cycling compared to the unwashed cathode. However, its cycling stability is still lower to be used in the practical cell. Therefore, we should further increase the long-term cycling performance by the other treatment. And this is the thermal stability of a prepared cathode. As you can see that the niobium and the tungsten doped cathode slightly improved thermal stability compared to other cathodes. However, I believe that after long-term cycling performance, after long-term cyclings, and niobium or tungsten doped cathode, further improvement in the thermal stability too. And this is a summary of niobium doped NCA cathode materials. Niobium doping contributed to first in maintaining the rod-shaped morphologies by impeding coarsening of porine particles. And the second is the retarding the migration of a transition metal, retaining concentric gradient profile wells. And the third is providing protection of a coating layer against the electrolyte attack, especially in the HF. And let me introduce the fluorine-coated niobium-doped NCMA cathode materials. We optimized the niobium-doped cathode material, the composition like this one, niobium doping amount 0.5 mol%. The optimized cathode used denoted as the unwashed cathode. And then we did treat the deionized washing called the DI washed cathode. And the third cathode material, deionized water washed and fluorine coated niobium doped NCMA cathode, denoted as the DIF washed cathode. As explained before, residual lithium issue is less pronounced in small cell with lower loading levels. But when the loading level increased and or the cell is cycled at the elevated temperature, the problem is pronounced. And this is the, as you can see here, residual lithium amount is increased with increasing nickel content, especially nickel content more than 90%. And as you can see here, the NCM 811 cathode material stably cycling up to 1,000 cycles without washing process. However, in the nickel-rich cathode, nickel content more than 90% cathode material shows the severe capacity fadings. And also this is the gas evolution as a function of a cycle lamp, and generated gas from the decomposition of the residual lithium lead to cell swelling, which result in poor cycling performance. Therefore, we need tools near surface stabilization by removing residual lithium compound and the coatings. And we wash the cathode material using the deionized waters, and also we provide LIF coating layer by reacting ammonium chloride with the remained residual lithium on the cathode surface. And as you can see, the CPSEM image, again, niobium doping induce readily aligned nanorod prime particles. Oh, what happened? Okay, it's okay. It's gone. And can you move on? Next page. Okay. Can you? If I push this button, the screen is gone. Oh, again. Something happens. Oh. Mm. I cannot see these screens. Okay, can I go to there? Mm-hmm. Sorry. Oh, it's okay. It's gone. It's appeared. I'm sorry for you. Okay, it's good. Let's move. Let's keep going on. This is a long-term cycle performance and the swelling of the pouch type full cells. As you can see, okay. As you can see here, and as you can see, the unwashed cathode shows the rapid capacity fading during cycling, and also the pouch cell containing unwashed cathode increase rapidly in cell volumes, and dry washed cathode exhibited improved cycling stability, slightly reduced gas generations. as expected, the cell containing DIF washed cathode demonstrate outstanding capacity retention of 92% with the least gas generations. And this is the DQDN curves. And as you can see, DIF washed cathode shows the smooth DQDN properties. And we believe that the gassing with the cell deteriorated the mechanical contact between the electrode, especially cathode, and the electrolyte, and thus leading to capacity fluctuations and eventually leading to capacity fadings. And as you can see, the capacity fading number point is clearly well matched with the cycling performance, as you can see here. And also, we believe that the excellent cycling stability of DIF washed cathode with the least gas generation is ascribed to the synergistic effect of both niobium-induced rod-shaped morphology and LIF coating layers. And this is a TEM and top seams image after long-term cycling. After long-term cycling, so we can still observe fluorine-rich layer both in particle outer surface and in the grain boundaries. And also, and as you can see here, we can observe the PO2, POF2, LiF2 Ni-ion from the top seams image due to the decomposition product of the lithium salt. We also observe the C2HO Ni-ion, which is the solvent decomposition product. As you can see, this is a DI washed, this is the DIF washed cathode. This is a CEI layer. As you can see here, decomposed organic and inorganic product, DIF washed cathode is mostly concentrated on the near surface, outer surface, suggesting CI layer of the DIF washed cathode much thinner than compared to the DI washed cathode. Based on this result, we believe that the performed LIF coating layer protect the cathode surface from the direct contact with the electrolyte by forming robust and thin and robust CI layer, and prohibit electrolyte decomposition, and thus greatly improve the cycling stability. And this is a post-mortem analysis of the prepared cathode after long-term cycling. As you can see from the HRTM image, the thickness of the rock salt impurity layer of DI washed cathode is reached to 45 nanometers, whereas that of the DIF washed cathode limited to below 14 nanometers. And also, SSRM image of the DIF washed cathode shows that the entire particle is nearly electronically active, whereas that of the DI washed cathode clearly shows that nearly zero electronic conductivities. And as shown, top seams 7 lithium mapping. This is a charged state, fully charged state. As you can see here, some 7 lithium was observed in the particle interior in the DI washed cathode. However, in the case of DIF washed cathode, you can see no 7 lithium is observed from the throughout the particles. And again, I believe that the performed LIF coating layer can effectively mitigate electrolyte decomposition and protect, and thus protection of the cathode surface. This is my conclusions. And among doped cathode materials, niobium-doped cathode will preserve larger shape Brownian particles, which can increase the highest mechanical strength and provide the least microcrack formations. Niobium doping was very effective, not only suppression of Brownian particle coarsening and Intl diffusion of transit metal, especially nickel, but also provide chemical protection as a coating layer from the HF attack at the grain boundary. The performed LIF is impede the decomposition of liquid electrolyte, preventing formation of electrolyte byproduct and thus suppress gas generations. And the combination of niobium doping and LIF coating can significantly extend the cycle life of a nickel-rich cathode to satisfy energy density durability of safety for next generation lithium-ion batteries. And this project was supported by the CBMM. I'd truly thank for the CBMM strong support. Thank you for your attention.
Okay, thank you for all of the speakers. We now have a 15-minute refreshment break, which I believe will be back upstairs. Okay. Okay, thank you very much for coming back. We ought to make a start to keep reasonably on time. So the next speaker is Dr. Bin Li, who's the Senior Vice President of Product Development at Wildcat Discovery Technologies. Wildcat is someone who's worked with CBMM for quite a few years, and Dr. Lee's been involved with inorganic materials for a considerable period of time, developing various different types of energy materials with a focus on batteries recently. And this morning he's going to tell us a bit more about how niobium plays a crucial role in next generation cathode materials. Okay?
Thanks for the introduction. Good morning, everyone. I hope everyone get recharged. Let's get started. Okay. Today, first I want to thank you for CBMM for the invitation. It's a great honor to be here and meet all of you guys. And today I will share Wildcat Discovery Technology on cathode development. And we'll focus on two different cathodes, lithium manganese iron phosphate, LMFP, and disorder rock cell, DRX. So I will start with a short introduction of Wildcat Discovery Technology. Some of them may not know Wildcat yet. And then focus on how niobium role in the LMFP and the DRX. There's two next generation cathode materials. So Wildcat was founded in 2006 in California in the United States. We currently have more than 100 people, including most of them are scientists and engineering. Our initial core technology is high throughput platform, which I will explain a little bit. With high throughput, we work with whole battery chain for the R&D research development. And currently we have more than 20,000 testing channels. And all of those hardware and software developed by ourselves. We design all of those hardware, software. And so all of the testing will be very flexible. We can handle all of the data by ourselves with our data science team. That would be second potential collaboration with customers. We can provide those battery testing service. For example, right now we are work with Microsoft for their battery testings. And we also recently developed those pouch cell line. We have two lines. One is 2 amp hours, and the second one is 20 amp hour line, and along with the electrode coating. So from this part, we can also provide those services. So for example, we can provide coated electrode film for the customer, or make the pouch cell, including dry cells or final cells for the customer to do testings. And the last one is our recently new business model. We are moving to new cathode materials manufacture in the United States, which I will talk about this more too. So that would be our third business model, provide cathode materials. And our pipeline for the cathode material will be lithium iron phosphate, and then MFP and the DIX. Those are three different cathode materials. So as I mentioned, WCAT core technology is high throughput platform. What does the high throughput platform mean? It means we can run hundreds or thousands of experiments in parallel. Say, for example, you can synthesize different NMC with different composition or different synthesis conditions, hundreds or thousands experiments in parallel. And also, of course, we can test many batteries. That's 1,000 battery easily for us to test. Those 1,000 batteries are different. They could have different cathode, anode, electrolyte, conductive binder, or conductive carbon. You can change every component of the battery. So you can do a much wider screening of every component of the battery. And currently we have, as I mentioned, we have 20,000 testing channel. We finished 500,000 experiments by using this high throughput platform. High throughput mainly by the automation, so it's not manually do those 500,000 experiments by automation. And as I mentioned, we moved to the cathode manufacturing in the US, but this high throughput platform still help us to work with our customer, which are cell maker or OEM. So we can use those pouch cell line that validate our high throughput technology. We can, when we provide it to the customer, it's not high throughput data, it's actually the pouch cell data. And also we can use this high throughput platform for our customer cell maker to down select which cathode you should use, which conductive carbon you should use in terms of both cost and the price. Although that you can use high throughput, you can screen a lot of the variables, which I will explain a little later. And also, you can optimize the battery performance. So even with the same 811, when you have different conductive carbon or different binder, different electrolyte, or even different anode, you could get a very different performance. We can optimize the whole system by using this high throughput platform. So right now, we have worked with more than 85 companies in the whole battery chain, finished more than 225 battery projects. And we generate 500 terabyte data. This is another advantage for the potential of WCAT. We can use this data for the machine learning and AI. That is our own data. We have all of those IP. We can use this, the real data for the machine learning, which is necessary for the machine learning. So we have worked with the whole battery chain besides just academic. Our customer including raw materials, battery material supplier, cell maker, and OEM. And here I just give two examples. Especially for CBM, we started with work with the CBM since 2012, and continuously, there's no stop. We have worked on this with CBM for many years. I really appreciate to take this opportunity for the CBM support, especially for DRX, which I will talk about more. And also, we work with the BMW more than already now 11 years. And for the BMW, mainly focus on the benchmarking for the cathode materials or anode materials. Now, as I mentioned, our third business model is cathode manufacture in the US. Why do we want to do the cathode manufacture? Because there's a need, especially in the North America. Here's data showing the forecast, the demand and the supply in the North America. We know for the EV battery, there's two major categories, NMC and LFP. This forecast is done by McKinsey. If you have the EV car in 2030, only have 45% of the whole sales, then that would be the slow adoptions for the forecast. 45% in 2030. But right now, China already passed 45% of the EV car of the total new car sales. And the middle one, black one, this is assumed 55% penetration. And the blue one is 65% penetrations. And the bar here is showing the demand based on the current capacity and also the future announcement. You can see in the North America, for the NMC, the demand probably will be satisfied by the current announced capacity. But if you look at FP forecast, they're similar to the NMC. At a later stage, you see 2030, you will have a little higher demand for the LFP than NMC. That is actually the trend happened in China right now. LFP already passed NMC in terms of the EV battery demand. But you can see in the North American, the demand of LFP there's a big gap between the demand and the supply. At least, even with the slow adoptions, you still have more than 50% gap. That's why WCAT decided to work on the LFP cathode manufacture. Of course, those LFP is currently quite a mature technology in China, and we will see probably even in the US, in North America, probably 3 to 5 years later, that's already also very popular in the US. Then we need to look at the next generation cathode. That we'll talk about. So in the WCAT, our pipelines start with LFP. We plan to start a manufacture in 2020, end of 2026. Then next generation lithium manganese iron phosphate start in 2027, 2028, then DRX in 2028, 2029. That's a kind of a timeline. Why do we choose those three different materials? All of those three materials are cobalt and nickel free. So it's environment friendly. All of those have relatively low cost because those either have pure iron. This mainly is manganese rich. And this is manganese and iron. The cost should be much more expected. And also, all those three materials, we know the safety of the LFP and the MFP. And actually, DRX has also much better safety than the high nickel materials, which need to further demonstrate in large format cells. I have some small set of data to show that indications of the DRX in terms of safety. And the last one, all those three materials could be manufactured in the similar process. So currently, LFP made by bit mill, spray dry, calcination, then jet mill. Those are four major steps. LFP, MLFP, you can make it the same way. DRX, we are designed in the same way to make this material. So all of the learning right now, we are producing LFP will be directly applied to our DRX. This will speed up the DRX from the lab scale to the manufacturer. And also, you notice we have those numbers in terms of cell energy density. This is on the cell level. You see those two numbers. It depends on what anode you're using. Start with the graphite, then end with the lithium. You have very different energy range. Same thing, but if you look at all of the three, you can see DRX has much higher energy density at the cell level compared to LFP or MLFP. And also, it's even higher than the high nickel. And of course, the lithium metal still a little farther away. If you just look at the graphite, you still have the very high energy density. Now, I move to the first cathode lithium manganese iron phosphate. These materials actually, I had worked on these materials in 2012 and 2013 for a couple of years by using our high throughput platform. Our high throughput platform still have those general 7 steps as traditional research. You start with the experiment design, then synthesis, then making the electrode, then formulate electrolyte, then assembling the cells and testing, then analyze the data. Then you do this circle. But with high throughput platform, we can design 500 experiments or more than that at once. Then you run those, because high throughput, it can run those things much faster. You do one circle, it's faster than traditional way, and also you get much more data. So you can learn from that data to do new design, which is very unique, not only based on literature or other people publication. You generate our own data, which is new. Nobody else has those. So that is like your snowball. You're running, getting bigger. You're learning more new things. Here I just give one example for the lithium manganese iron phosphate study. And in 2012, at that time, we worked on the 80% manganese. Currently, in China, most of them still work on the 6% manganese. Here I give for the doping study. We have those baseline, and then doping A elements and doping B elements. You can see that doping does improve at both initial capacity and also cycle life. And then we do, as I said, this is the first round. We do this one, we learn from this, and do the second round, those high throughput screening. So we combine those A and B dopings. Of course, as A, B could be very different transition metal or main group metals, right? They have a different function. Now, then you see the synergetic effect when you have the doping A and B. And here, you see you get a much better cycle life. Initial capacity also improve a little bit. For these materials, we know the conductivity is not good. The carbon coating is very important. So we use our high throughput to do the carbon coating. That's including different type of carbon coating conditions of those variables. Then you will see we can make further improvement in terms, especially for initial capacity. You get almost 150 milliamp per gram and much better cycle life. Then so this is another round. With this high throughput platform, after you lock down the compositions, the carbon coating, you want to fine-tune the synthesis condition to make the material. Here, we do further optimization by optimized synthesis condition. You can see you get a further improvement in both capacity and the cycle life. So this is showing how this high throughput platform works. And we can work with different customers for the battery materials development. Now, here's just showing a little data showing demonstrated for these materials in both half cell and full cell. For these materials, especially when you have very high amount of manganese, the elevated temperature performance would be the key. Here we demonstrate at 50 degrees C in both half cell and full cell. Here, still with YCAT high throughput cell, which is quite small cells. We demonstrate 400 cycle, but then this one was work with a customer, and they made 10 amp hour pouch cell. They were able to reach 700 cycle at 50 degrees C. So this is critical for the MR4P at elevated temperature performance. So this is another evidence to say when you use high throughput, you can down screening the selections, then demonstrate it in the large format cells. For the high throughput, you find it's not only one solution. Say, for example, I started with 100 different design. I logged down to 10 or 5 different battery recipe, then you demonstrate in the large format cells. Otherwise, if you start with a large format cell, the cost, timing would be cost very high, timing very long. Yeah. Now, I want to demonstrate some of the niobium effect in the lithium manganese iron phosphate. Here we have different doping elements, but it depends on which side you dope. So here showing, this is the baseline. Here we're showing the doping on the manganese side, and there doping on the iron side. We show the different key metrics here, 0.1C discharge capacity, 1C discharge capacity, and 5C discharge capacity. The dashed line showing the baseline for each at each rate. We have 7 different kinds of dopings, including niobium. You can see in general, you see on the magnesium side, niobium showed improvement on all of those rates. And But for the iron side, niobium is only element that show those. Niobium has much more flexibility or more robust in terms of the doping study in these materials. You do see quite a big improvement, especially for the high rate, which is critical for the EV or in the future for the power application like a data center. This is very important. So here just show the doping element. So actually, when we do the experiment, I said we do those high throughput screening. You can do many experiments in parallel. What we do is you change all of those variables because we know everything that matters. Different precursors will affect, and definitely niobium amount, and also we show the doping side. Here we show the data showing the cycle 1 capacity and the 5C capacity retention. The color showing with different niobium precursors. So with each color, you might have different niobium doping amount or different synthesis condition. Here you can see those blue color showing the best in terms of cycle 1 capacity and also 5C rate capability. So that's, if you can't say, for example, I use 3 to 5 different precursors and 3 to 5 different amount, and then 3 to 5 different synthesis conditions, the combination number is quite huge. With the traditional way, you just cannot do it. But with our high throughput, we can do that. So this further demonstrates for the niobium doping study here showing, here also is cycle 1 capacity and also energy density, because what matters is energy density. You can say all of those niobium or niobium with double doping with element A, you show the best performance in terms of both capacity and energy density. And actually, the energy density you can see here is showing because you have average higher voltage. It's showing the baseline when we started this project with the CBNM. Again, Sunset CBNM sponsors these ones. Even with compared to the commercial MFP, which come from in China, we can still make further improvement in terms of the average voltage on the CO20 rate or even at 1C rate. Now, to the last part for the DRX cathode. So this part, DRX, I guess most people are very familiar with the lead oxide, which have all the materials. For the DRX, you will have both lithium and transition metal occupy the same site. But lithium diffusion is, you can see, lithium in the octahedron, but the diffusion through those tetrahedral side to the next octahedral side. This is showing you will have much smaller volume change, which I will show that data later, which is one of the advantages for this type of the cathode materials. And I think right now, high nickel is still give the very high energy density. It kind of reached the limit, and especially also in terms of cycle life and also safety, which Professor Sin talked about quite a bit. But still, nickel still dominate in terms of energy. For the long-range car, you still have to use this high nickel and MC. And for the DRX, it's a study, this material was discovered in 2015. This material started with niobium. Here you see this powder is white. It means it's a semiconductor. It's not conductive at all. But if you dope in this element, niobium, with different transition metal, here it's manganese, nickel, cobalt, and iron. You can almost, for this material, you can almost dope in any elements, transition metal in the periodic table. Literally. It's very rich chemistry. There's a lot of work can be done. But you can see this material started with very high amount of niobium. But why do we want to work this material? This material does show a higher energy density in terms of gravimetric, almost 50% higher than high nickel, 85% nickel. And the volumetric energy is the difference is a little smaller because of relatively low true density. These materials also show the better safety, which I show some data later. Now, why do we actually need niobium? Our data showing niobium is necessary for the DRX. This is the first time I show this data in public. But you can see here, we have 3 different compositions. As I said, this material is very rich chemistry. There are so many things in play. So in this here, from the left to the right, niobium amount is reduced. And here we have CO20 capacity and CO3 capacity. You can see the capacity decrease significantly when you reduce niobium amount. And even no matter what range you're playing with the DRX, you still see this trend. So when you don't have enough niobium, you will not get high enough energy density. I think like those, we are industry company, so we don't spend much effort to understand why, but I think there's a good area for academic to do the research, understand why. But for us, we need the results to move forward. Here's a little more detailed example here showing even when you go to niobium 0, you see those capacity is the difference, the capacity is huge. Niobium play a very important role. Even you just look at cycle 1, could be efficiency. That's without niobium, you only get 81%. With niobium, you can get 90%, which is enough as cathode materials. So again, there's a lot of work can be done by the academic research to understand why. 2 more things that I want to emphasize is for this DRX materials, the safety compared to the 811. Here is the DSC based on the cathode. You see here is with NMC, you have the heat generation in very short time, which means there's heat generation. Easily the trigger thermal runaway. And for the DRX, the heat generation is much slower. And more important, if you look at those onset temperature, DRX is much higher than the NMC 811. And total heat generations, DRX is much lower than the high nickel 811. And this on the cathode. If you cathode fully charged to 100%, that's the data. And then what about the full cell? Here we do show the full cell. You have the both cathode, anode, electrolyte, and compare the difference between DRX and NMC. You still see the same trend, and also you see the same much higher onset temperature of the DRX compared to the high nickel, and also much lower heat generation. One more slide showing is for the oxygen release. So for the high nickel ones, one of the dangerous things is oxygen release. When you have the cells, have good sealings, in order to catch the fire, you need oxygen. You need a fuel which you have. See, here we're showing when we heat up those cathode material, for the DRX, we do not see any oxygen released, even up to the 600. But for the NMC, you do see the oxygen release between like 220 degrees C. And we do see some gas generation with DRX, with our current DRX. What we see is you have relatively large amount of those CO2 generated. That is because our current DRX still have like a 4% carbon content. And we use, say, how do we confirm this is come from the carbon, not from you generate oxygen, then react with the electrolyte, then generate CO2, right? That's still possible. What we do is you chemically isolate the DRX, and you don't have the carbon. And here you do see the oxygen is still zero, the CO2 amount is very little. This further confirm there's no oxygen release. And the CO2 amount come from the carbon of the DRX coating. So last one is about the volume change. As I mentioned, because of those lithium diffusions, there's a small volume change. We also demonstrate those. You see here's a cycle number with different charge voltage windows. You can see charge and discharge, you get the 3.3% volume change. Even five cycle, around 4, even 100 cycles, still 3.7 between charge and discharge. That's the swell of your battery. This is compared to Professor Sen shows those 811 probably 5.8% volume change. This is smaller. And also we do not see, even after 100 cycle, discharge DRX shows the volume almost 72%, which means those materials are actually quite stable. So I think there's another big advantage. It's better for the future solid-state battery, which require very small volume change. Yeah, so this kind of summary, I think for the DRX, it has very high energy density, and it's cobalt nickel-free, more stable, which gives you much advantage in terms of pack energy density. That's why the LFP can challenge the NMC, because the pack energy density could be getting close to the NMC. And also low volume change and also faster charge capability. We do see the niobium play a very important role. Thank you for your time. Sorry for that.
Okay, so we've got some time now for some a Q&A session. So can all of the speakers from this morning come up to the front and take a seat? There's a microphone there as well. So the other 3 speakers from this morning, if you could come up to the front, sorry. Yeah. Great, okay. So you have a microphone there to answer the question. So does anyone want to kick off and ask a question to any of the speakers or a general comment? Yes, there's a question over here. I don't know if we have a microphone for the audience as well. Ah, we do, yes, someone's coming. Hello.
Hello. Thank you. Kane Carty, Wood Mackenzie. Thank you all for your presentation this morning. It was quite insightful, and I think it seems like niobium does have some fairly useful prospects in both cathode and I'm sure anode this afternoon. Kind of 3 questions really, more on the supply chain more than anything else. On the demand side, how much of the kind of global cathode market are you expecting to utilize niobium, either doped or coated? Second part on the supply, what risks do you see on supply chain security for niobium oxides? And sorry, third question, if you will, excluding any savings made on niobium processing, what are the associated additional costs that cathode producers will need to factor in when considering utilizing niobium doping?
Okay, who wants to go first? CBMM.
I think the question, the number 1 and 2 is more to CBMM. So the projections that we have about the penetration of the market as niobium as additive for different chemistry until 2030 is around 38% of the addressable market. And the addressable market is 50% of the total market. So if you take all the cathode production materials, 50% is our addressable market, and our intention is to penetrate around 40% in this market, okay? And what is considering the addressable market today, okay? Chemistry as presented this morning, like LMO, LMFP, nickel, mid-nickel, high nickel. LFP, we have studies and development, but we did not consider it yet. If we start to have good results on that, our addressable market is going to be higher, and for sure we're going to have higher volume. It's not considering DRX as well, because it's a new chemistry, low TRL, so this is evolution that we can have in the future, okay? But this answer your number 1 question. The reliability of the supply chain on oxides, so we mentioned that today we have more capacity than the market demands. So we sold for cathode this year 1,000 tons. and we are putting dedicated capacity around, in the next 2 years, more 5,000 tons. And until 2030, more 20,000 tons. So we're gonna have for the battery around 25,000 tons of oxides, and our projection, and we hope, and we are working hard, an event like this, that we fulfill this capacity until 2030. And then we start in the following 2 years, what would be necessary for more. We hope that we can even bring more. But this is part of the DNA of CBMM, always put capacity in advance, because we create the stability to develop the technology. And also we are studying right now through our partners, to invest as an enabler in the supply chain of cell manufacturing as well, because we believe this also is a need to speed up the technology as a cell manufacturer, more what we're gonna talk in the afternoon in the anode side. Okay, and the third question I will leave to the experts here, because they're gonna answer more than me. What is the impact of the cost of niobium, and what is cost and benefit for that? Okay.
Thank you.
I can answer a little bit about related to DIX. So DIX mainly elements is manganese. Of course, it's a lithium rich. That's why you have the high capacity. And the lithium carbonate is kind of the dominant price for the DIX. Then the manganese is quite cheap. And we do have a certain amount of niobium, which we do not disclose yet, but you can check our patents. As I show in initial, when people work on the DIX, initial niobium amount quite high, like 0.2, 0.25, 0.3, which means probably like more than 30%, probably 0.3 equal probably 40%. It's very high, but we reduce those amount. That's where you can do the chemistry. You have the balances in terms of future cost and also performance.
For MO, maybe I can make some comments for niobium MO. Actually, when we talk about the cost or price, I understand it's based on the how great you can increase the performance. You see, MO compared with the other cathode material is the cheapest one. It's cheaper than AFP, NCM, and other kind of cathode material. So for this kind of cathode material, the MO maker, the industry, choose niobium as the solution. That means the cost should be not a problem for other cathode, I believe. Okay.
The other speakers at this stage, or? No, just a comment. Oh, Rogerio, yes.
No, and in terms of processing or industrial capability so far, and then maybe they can also provide comments. Niobium as an additive is pretty much a drop-in solution. So you do not need any special process capabilities to use and to apply niobium. Of course, you may need to change some process conditions in terms of maybe temperature, washing steps, and how you incorporate, but there is no special need to have any special equipment. It's pretty much a drop-in solution. And in this addressable market, depending on the formulation, we are working in the range of 0.3% niobium addition up to 0.7, 0.8% niobium addition is the necessary amount of niobium. More than that, as we could see here, we can have even bad effects. So that is not necessary, okay? But it's pretty much a drop-in solution in terms of cathode. For anode, we are going to see in the afternoon is a little bit different, but for cathode, that is pretty much the expectation.
Thank you. Any other comments? No? Okay. Does anyone else have a question or a comment they'd like to raise? Yes.
Hello, thank you for your presentations. I'm Alexandra Mikhail with IQ Technologies. So my question is a bit general. You've all presented the effect of niobium oxides in different materials. My question is, has any of you detected a certain trend regarding niobium size, like micron, nano, or anything larger? And is there a specific crystallographic phase that is significantly more beneficial than the others? Is there any clear trend in the literature right now? Again, for additives or coatings.
I can give kind of a cop-out answer. So I showed that my process to make NMC is a little different than conventional processes. So all of these questions that you're asking about particle size, phase, we're working through that right now. So I can tell you that I have 2 people right now trying to answer that exact same question about particle size, whether that's for a dopant or for a surface coating today. The data I did show today was all about micron-sized niobium as a surface coating at 0.1, 0.2, 0.4 weight percent. I have also data that I'm not showing today purposefully for nano-sized niobium surface coatings with the same loading, and they did not perform as well as the micron size. So as today, very early days, micron for surface coating on NMC, at least NMC produced via an all dry zero waste process, is a little better than nano size.
Okay, any other comments? Okay, another question. Yes, Robson. Okay, all right, you can answer the question.
I'm also for CBMM, yeah, I work in cathodes, yeah. Yeah, definitely, I think the way that we are customizing our products in order to really see the particle reactivity for either doping or coating, yeah, as you said, the crystal phase, particle size, yeah, those are very key. Yeah, I think a general trend in terms of reactivity is smaller, and the lower temperature crystal phases in terms of better, in terms of reactivity. Yeah, it's not surprising what Mark said about the coating, that the micro size is better coating because maybe you can have a lower amount, is a better coverage of the surface when you have a little bit, depends, the way that you prepare. Yeah, there is some trends also, people working on amorphous phase of niobium oxides with high surface area, depends on the process, and also can have very good coatings in the materials itself. Yeah, for nano sizing, I think the learnings that we are having is a good for doping.
Thank you. Yes, question at the front here as well.
Yep.
Hi, this is a question to Dr. Bin. How far are we from market maturity on the DRX technology? Because that sounds very impressive from your graphs.
Yeah, I have limited information I could share, but I think in general, we're getting very close to be commercialized. As I said, right now it's still in the lab scale, about 1 kilogram batch size. We do have the plan probably manufacture in the 2029. Yes.
Thank you.
Good, thank you very much. Okay, I can see no more hands up. We're running a little late, so I think we should perhaps close this session now, and the speakers will be around over lunch and during the afternoon if you have any more questions than this. So perhaps we can thank the speakers from this morning now. Great, thank you very much.